Hi, this is Saravanan R, Assistant Professor, Department of Aeronautical Engineering. In this particular video, we are going to talk about cruise flight performance, nothing but a steady level flight from flight dynamics. Flight dynamics is one of the most important subjects in aeronautics. So before getting understand what is flight dynamics, let us understand the basic forces which is acting on the aeroplane. There are four forces which is acting on the aeroplane. The first one is a lift, and second one is drag, and third one is propulsive thrust, and fourth one is weight. So lift is which is perpendicular to the flight path. Drag is which is parallel to the flight path. Propulsive thrust which is almost parallel to the flight path. So weight is always vertically to the flight path, and then it is centered toward the earth. So we are going to apply Newton's second law on the airplane, which is in curvilinear flight path, so that we can derive our equation of motion. So before getting into that, we must understand what is Newton's second law. So Newton's second law we call this law of motion. So that is, if in mathematical formulation we can call it as a F is equal to mass. F is equal to mass into acceleration. So F is forces acting on the airplane, mass is mass of the airplane, and A is acceleration of the airplane. For unaccelerated level flight performance, nothing but a cruise flight performance, so the dv by dt, that is always becomes zero because it is unaccelerated. It's maintained at a very constant speed. So the equation of motion which is derived for the aeroplane based upon the angle which makes is t cos epsilon minus d equal to 0, L plus t sine epsilon minus w equal to 0. Since our flight is unaccelerated and with very much in a steady level flight conditions, the angle which makes also becomes 0, which is small. So the equation will be reduced to L is equal to W, thrust equal to drag. So L is equal to W means the lift is equal to weight, thrust equal to drag. So lift is equal to weight means, and the weight of the airplane is contracted by the lift produced by the airplane, and thrust equal to drag means the drag produced on the airplane will be contracted by the engine, thrust produced by the engine. So the lift and the drag, lift and the thrust should be maximum than the weight and drag of the airplane. So this is your level unaccelerated flight. So the aircraft flying at a very constant speed, the sum of forces acting on will be zero. That whichever two perpendicular directions will be contracted with each other, as you see in the last slide. That is thrust equal to drag, lift is equal to weight. So the entire weight of the airplane is perfectly balanced by the lift, and the thrust produced by the engine will also be totally contracted by the drag on the airplane. So, this is your velocity equation. So, velocity of the steady level flight. For a steady level flight, that is, we know the condition: lift is equal to weight, and that is L is equal to W. So L is equal to W. This is your normal lift equation, that is CL half rho V squared S. So if you interchange means, you will get V squared is equal to 2W rho SCL. V equal to root of 2W rho SCL. So the stalling velocity is that when your CL gets maximum, you're reaching your stalling velocity. So that is what is mentioned here. So this equation is your equation number 1, is your velocity for a steady level flight. So there are a number of parameters that are there to analyze your airplane performances. So the first one is wing loading. So wing loading is nothing but the weight of the aircraft by weight of wing plane form area. So the wing loading is small w is equal to weight by surface wing plane form area. For a steady level flight, we know the velocity equations. So velocity, so we already derived it. So this is your normal velocity, and this is your stalling velocity. The thrust loading, T by S, and the thrust loading is the product of thrust to the weight ratio, and thrust to weight ratio and the wing loading. So T by S equal to T by W, W by S, you will get your thrust loading. So this is your thrust required. This is one of the important equations in cruise flight performance, are nothing but a steady level flight. So what is thrust required? So based upon the equation motions we derived, that is T is equal to W, T is equal to D, sorry, T is equal to D. So that is thrust equal to drag. So thrust equal to drag means the drag on the thrust produced by the engine should be more than the drag on the airplane. So this is very much necessity for airplane power plants to produce the thrust which is more than the drag of the airplane. So so we must understand what is the minimum thrust required. So for that, we are going to make an equation for that. As from that, we can understand what is the minimum thrust required. Based upon that, we will design our aircrafts. So for designing the aircrafts, for inserting and installing the power plants, to know what is the thrust required minimum and what is the thrust required maximum is a very important parameter. So thrust required thrust required equal to drag. So we are here we are multiplying and we are multiplying and dividing the equation with respect to W. So L is equal to W, that is for your steady load flight conditions. So your W will be there, D will come down, so L by D. So C will instead of L by D you can write CL by CD. So based on this equation, if a CL by DC is maximum, means your thrust required will be minimum. Okay. So how to understand the thrust required minimum? So on thrust required curve. So this is your thrust required curve. In y-axis we have a thrust required, and x-axis we have velocity. So let us understand how this graph has been drawn. So first we need to understand the velocity. We need to select the velocity, that is flight speed, v infinity. Then you have to put the velocity in CL equation. This equation already know the equation, that is CL is equal to W by half rho infinity v infinity s. So from that you can easily calculate the CL value. Then you can calculate the CD, that is CD is equal to CD naught plus CL squared by pi ER. So then calculate CL by CD. So calculate TR. So once you calculate for TR for this particular velocity, you can plot it here. So namely, you can calculate the TR for different velocities. Means you will get this graph. So this is your graph. It goes like this. So what you are interpreting from this graph is that at the initial velocity, the thrust required which is maximum. So at the velocity, as the velocity increases, the thrust required getting decreases. So it is getting to the point where you are at the it will become very minimum. That is the point where the L by D is maximum. That is lift is maximum than the more maximum than the drag on the aeroplane. So after that, the graph is increasing. That means the thrust required value is getting increased. So thrust required increase because of there are two things are there. First we need to understand that the drag on the airplane is classified into two ways. One is zero lift drag and drag due to lift. Okay, and initially your drag due to lift will be more, but as the velocity increases further and further, your zero lift drag will increases. So that is why after the L by D max point, your thrust required is getting increased. So this is the graph explains further information. So the same graph it is which you have seen in the last slide. So it has been given in a very prominent manner. Okay. So this is I'll explain for this is your y-axis that represents the thrust required. In this is x-axis that represents the velocity. So this is in this direction. This is the decreasing of angle of attack. So initially you have more angle of attack, then you have a less angle of attack, then you entering into the cruise flight performances. So this region is rapidly increasing drag due to lift as velocity increases, and the region of velocity instability, rapidly increasing zero lift drag. As the velocity increases, this is the region of velocity stability. So initially you can see that thrust required value is maximum because you have an angle of attack. You need to move from one altitude to another altitude, so your thrust required will be maximum. So drag due to lift also maximum. So as a as the velocity decreases, your drag due to lift also increases, because we need to move from one altitude to another altitude. We need to supply more amount of energy. So once your velocity increases, the velocities become instable. Instability actually instability. So it will reach the point where this is the point we call it as this point where the L by D is maximum. So that point is correspondingly point we call it as the thrust required minimum. So L by D max point and thrust required minimum point. So after that, what happens is that your zero lift drag increases as velocity increases. So this graph steeps on increases. So drag versus flight velocity. So this is drag versus flight velocity. This is your same graph which we are seeing this. We are trying to interpret in a further way. So that is your full graph. This is your full graph. This is the graph due to lift, and this is your graph due to zero lift drag. Okay. So that is namely we call it as parasite drag, or this the drag due to lift we can call it as the induced drag. So zero lift drag is proportional to v squared, and drag due to lift is proportional to v one half v squared. 1 by v squared, sorry, 1 by v squared. So 1 by v squared means even when the velocity increases, the drag due to lift decreases. As the velocity increases, zero lift drag increases. So this is one of the main interpretations. So why we are getting increased drag as the velocity increases. Uh, so how fast we can fly is that when the maximum flight occurs when the thrust available reaches the thrust required. Okay, so when the thrust required reaches the thrust available, means that is the maximum point where that is the maximum thrust the airplane can produce. That's where you can reach your maximum velocity. So after that there is no thrust available, you will not reach any further velocity. So this is your for your information. And then next, minimum drag conditions, one of the parameters. Based on that, the designers are able to design their aircrafts. So for minimum drag, L by D value should be maximum, so drag minimum equal to W by L by D max. To obtain this condition mathematically, CL by DC, in order to say CL by CD to be maximum, so we should differentiate it and make the equation to 0. So once you do all those mathematics, means you will get CD naught minus KCL squared. So it will end up as CD naught equal to KCL squared. That is the meaning is this: zero lift drag coefficient is equal to drag due to lift coefficient. So that meaning is that in order to L by D should be maximum, your zero lift drag should be equal to the drag due to lift. So the point is where you will get your thrust minimum, that is minimum drag also occurs. That's the point where your L by D also getting max value. So then if you interchange this equation, you will get CL is equal to root of CD naught by K. So the so from drag polar equations, we need to find what is the minimum drag condition, minimum drag equation. So this is your drag polar equation, that is CD equal to CD naught plus KCL squared. So if you substitute it to the equation number 2, which you already seen in the previous slide, that is CD naught equal to so CD equal to CD naught plus K. So CL squared we already derived it from the previous slides, at CD naught by K. So you will get CD equal to 2 CD naught. From that you will get L by D max value, that is 1 by 1 by 2 root of K CD naught. From that you will rearrange, means you will get D minimum equal to 2L root of K CD naught. This is your minimum drag equation, the drag minimum equation, that is 2W root of K CD naught. Then we are moving into finding what is the velocity corresponding to the minimum drag. So the velocity is equal to root of 2W rho SCL. CL is equal to, you know this one already we derived this condition, CL is equal to root of CD naught by K. V minimum drag will equal to root of 2W by rho S K CD naught by 1 by 4. So this is your velocity corresponding to the minimum drag. Okay, so this is the one line which to wholly represents the minimum drag conditions. In order to have a minimum drag, your thrust, even if in order to have a minimum drag, your thrust required should be minimum. So in order to have a thrust required minimum, the L by D value should be maximum. So this is final conclusion we are trying to make. So minimum control condition, there are four to five conditions are there. The first and foremost condition is to have a minimum drag. L by D value should be maximum, and then your zero lift drag should be equal to drag due to lift, and then this is your L by D max equation. Then this is your drag minimum equation, and then finally your velocity corresponding to the minimum drag. So this for this video we have seen up to minimum drag conditions. So this is the basic ideology to analyze your aircraft. So from this, the person who's designing the aircraft know how to have a minimum drag conditions on his airplane. Thank you.